Just before sunrise on December 19th, something happened near Earth that changed everything we thought we understood about 3I Atlas. It wasn't the brightness that stood out this time, it was the angle. For the last several days, observatories around the world had been watching the interstellar object draw closer, its tail fluctuating, its emissions rising, and its behaviour becoming more erratic. But this morning, the anomaly was not in the tail, nor in its jet activity, it was in its alignment. 3I Atlas, for the first time since entering the inner solar system, rotated to face the sun directly. Not in a loose or tumbling fashion, not like a comet spiralling from thermal stress. This was controlled, measured, deliberate, and it held that position. What followed over the next few hours wasn't a burst of radiation or a surge of particles, but something far stranger. The entire comet began to behave as if it were responding to external forces in a highly synchronized way. Earth-based magnetometers, solar monitoring satellites, and deep-field telescopes all started picking up faint but coordinated changes in motion. And then the alignment held. It wasn't momentary. It locked. In the hours that followed, scientists around the world began sending urgent data packets to central repositories. This wasn't a comet veering off course. It was something recalibrating. And what it aligned to, the sun itself, was more than symbolic. Because the angle of its sunward-facing plane did not match the gravitational influence alone. It showed signs of intentional positioning, as if 3I Atlas wanted to face the sun. And as it did, Earth's upper atmosphere began to ripple with a pattern that hadn't been seen in decades. A resonance, a pulse, faint, but growing stronger. This episode breaks down exactly what happened this morning, how the alignment anomaly was first detected, what the jet behaviour tells us, and why some of the world's most respected astrophysicists are now questioning the very nature of this object. Because if this alignment wasn't accidental, then something inside 3I Atlas is aware of its position, and it just made a choice. Just before sunrise on December 19th, something happened near Earth that changed everything we thought we understood about 3I Atlas. It wasn't the brightness that stood out this time, it was the angle. For the last several days, observatories around the world had been watching the interstellar object draw closer, its tail fluctuating, its emissions rising, and its behaviour becoming more erratic. But this morning, the anomaly was not in the tail, nor in its jet activity. It was in its alignment. 3I Atlas, for the first time since entering the inner solar system, rotated to face the sun directly, not in a loose or tumbling fashion, not like a comet spiralling from thermal stress. This was controlled, measured, deliberate, and it held that position. What followed over the next few hours wasn't a burst of radiation or a surge of particles, but something far stranger. The entire comet began to behave as if it were responding to external forces in a highly synchronized way. Earth-based magnetometers, solar monitoring satellites, and deep-field telescopes all started picking up faint but coordinated changes in motion. And then the alignment held. It wasn't momentary, it locked. In the hours that followed, scientists around the world began sending urgent data packets to central repositories. This wasn't a comet veering off course, it was something recalibrating. And what it aligned to, the sun itself, was more than symbolic. Because the angle of its sunward-facing plane did not match the gravitational influence alone, it showed signs of intentional positioning, as if 3I Atlas wanted to face the sun, and as it did, Earth's upper atmosphere began to ripple with a pattern that hadn't been seen in decades. A resonance, a pulse, faint but growing stronger. This episode breaks down exactly what happened this morning, how the alignment anomaly was first detected, what the jet behaviour tells us, and why some of the world's most respected astrophysicists are now questioning the very nature of this object. Because if this alignment wasn't accidental, then something inside 3I Atlas is aware of its position, and it just made a choice. To understand why the alignment observed in 3I Atlas immediately raised concern, you have to understand what normally happens when any small body approaches the sun. Space is not empty. It is filled with light, charged particles, and momentum. The sun constantly emits radiation and solar wind, a stream of particles moving outward in every direction. When an icy body like a comet enters this environment, the interaction is one-sided. Heat strikes the surface, ice sublimates, gas expands, dust is dragged along, everything flows away from the sun. This is not preference or tendency, it is inevitability. That is why comet tails always point in the same general direction. Dust tails curve slightly because of orbital motion, but ion tails are rigid. They point straight away from the sun every single time. This behavior is so reliable that comet tails have been used as directional indicators for centuries. If you see a tail pointing toward the sun, your first instinct as an astronomer is not alarm. It is geometry. So-called anti-tails are well known. They appear when Earth's viewing angle aligns with the plane of the comet's orbit. Dust released earlier in the journey can appear to project forward, creating the illusion of a sunward-pointing feature. But the illusion is fragile. It vanishes quickly as the geometry changes. It never persists, it never strengthens, and it never shows structure. What was seen near 3I Atlas on December 19 did not behave like an illusion. The alignment held across multiple observation angles. As Earth rotated and orbital parallax shifted, the feature remained anchored, relative to the Sun rather than the observer. This alone ruled out classic anti-tail explanations. The dust plane geometry simply did not support it. More importantly, the material forming the alignment showed signs of active replenishment. It was not static debris left behind, it was fresh. Fresh material moving toward the sun is deeply counterintuitive. Any particle released in that direction should immediately be pushed back by radiation pressure. Even heavier grains cannot maintain sunward motion without continuous force. This means the observed structure was not drifting, it was being maintained. Comets do not maintain structure, they leak. Yet 3I Atlas held a coherent plume for hours. The feature did not fan out, it did not fragment, it narrowed. The longer it persisted, the more concentrated it became. That alone forced scientists to abandon the idea that this was a passive optical effect. Then came the thermal modelling. If material were being ejected sunward purely through sublimation, the surface region responsible would have to be significantly hotter than surrounding areas. Infrared observations did not support this. The sunward-facing region was not measurably hotter. In fact, it appeared slightly cooler than expected, suggesting rapid heat redistribution or unusually high emissivity. Both possibilities imply structure. The next question was whether rotation could explain the orientation. If the nucleus was spinning in such a way that a jet happened to align sunward briefly, that alignment should sweep across space as the body turned. It did not. The orientation remained fixed while the light curve indicated ongoing rotation. That combination should not exist. A rotating body with a fixed jet orientation requires internal stabilization. Either the jet is being actively redirected, or the surface geometry is constrained in a way natural rubble piles do not exhibit. At this point, researchers began comparing 3I Atlas not to comets, but to systems. Rockets, solar sails, plasma interactions. Not because they believed it was artificial, but because those were the only frameworks that produce sunward exhaust without chaos. Sunward orientation is rare because it is inefficient for natural bodies. It works against the dominant forces of the solar environment. It requires either extraordinary coincidence or continuous control. Coincidence fades quickly under repetition, and by the end of December 19, repetition was exactly what the data showed. The alignment was not a moment, it was behavior. Jetting is not rare in comets, it is the signature behavior. When sunlight strikes an icy surface, the volatile material trapped within begins to sublimate. Gas expands outward, dragging dust with it, creating plumes of activity that fan into space. These jets form irregularly, pulse in strength, and spin chaotically as the body rotates. Sometimes they trigger fragmentation. Sometimes they cause the nucleus to tumble. But what they never do, at least not in recorded science, is act with calm precision. The jets seen on 3I Atlas during its closest approach to Earth were not behaving like cometary exhaust. They were behaving like propulsion. The difference is subtle, but crucial. Exhaust is uncontrolled. Propulsion is regulated. On the morning of December 19, jet activity on 3I Atlas did not emerge from scattered locations across the nucleus. It originated from consistent points, narrow, repeatable, and synchronized across multiple instruments. Images taken from separate observatories across the globe, using different filters and timing exposures, showed the same pattern. Focused linear plumes extending from two regions on the surface. They did not wobble. They did not arc outward and curl away. They remained shockingly straight, almost vectorized. This is not what comet jets are supposed to do. One feature extended in the general direction of the Sun, the other along the orbital plane but slightly offset. The geometry remained consistent for over 6 hours, with minimal shift despite the known rotation rate of the nucleus. That constancy was the first anomaly. The second was the brightness distribution. Instead of gradually fading with distance, the jets retained brightness over unusual lengths, meaning the material was ejected with significant and sustained energy. Not just a burst, but a continuous push. Jetting of this kind requires pressure. Pressure requires force. Force requires either a large sublimation zone or a mechanism that concentrates energy. Neither explanation fits easily within current models of comet behavior. To maintain a jet that does not bend under solar wind pressure, the velocity of the particles must be extreme. Sublimated gas alone, especially from carbon dioxide, should not be capable of achieving this unless channeled through very narrow vents with structural support. That kind of collimation has never been observed in a natural comet. Further complicating the picture was the thermal footprint, or lack thereof. If these jets were the result of explosive heating, the surrounding surface should show elevated infrared signatures. But the areas adjacent to the jet sources appeared cooler than expected, not hotter. It was as if the heat was not being absorbed and spread, but redirected and concentrated. That redirection implies internal geometry. Natural bodies do not exhibit geometry. They fracture, they slump, they vent wherever cracks allow it. And yet, 3I Atlas showed behavior that looked more like guidance than rupture. The jets did not scatter material into space in a fan-like pattern. They released it in narrow channels, channels that defied rotation, wind, and the object's own momentum vector. In plasma images captured by the solar orbiter's instruments, the jet interaction with the surrounding solar wind created bow-like distortions, faint but measurable. These distortions were symmetrical, as though the jets had formed pressure tunnels in space, resisting collapse from the environment around them. Exhaust doesn't resist, it dissipates. Something in these jets was holding form. That led some scientists to propose that the jetting wasn't a passive effect at all. Perhaps it was a system, triggered by proximity to solar energy, structured to respond, not just endure. Perhaps the jets were the signature of adaptation, or perhaps, more unsettlingly, they were the signature of design. The jets coming from 3I Atlas were not subtle. They were long, bright and directional, and more importantly they were sustained. Not bursts, not flare-ups. They kept going, and that raised a question that scientists around the world were not eager to ask aloud. Where is all this energy coming from? In comet science, energy calculations are supposed to be simple. An object absorbs solar radiation. That radiation heats its surface. The heat causes ice to sublimate. The sublimation releases gas. The gas escapes, carrying dust with it. You measure how much sunlight is hitting the object, how much surface area it has, and what kinds of materials are present, and from that, you estimate how active the body should be. The problem with 3I Atlas is that the numbers don't add up. At a distance of just over 1.4 astronomical units, the amount of solar energy reaching 3I Atlas is known. It's measurable. It's a fixed quantity based on distance and surface area. Even if you assume that every photon of sunlight is absorbed, no reflection, no loss, the energy input still falls far short of what's required to explain what's coming out. The jets visible on December 19 weren't weak plumes. They had structure, they had pressure, they had persistence. And all of that takes energy. Real energy. Measurable energy. Energy that isn't accounted for by the sunlight alone. When scientists began to run the math, the problem deepened. You can calculate the energy required to accelerate gas particles to the observed velocities. You can estimate the mass being ejected by looking at the length and density of the jet structures, and you can integrate that over time to determine how much power the system is using. The results were disturbing. The energy output, just in the form of kinetic motion of the jets, was orders of magnitude higher than what the surface should be able to absorb from sunlight alone, and this wasn't theoretical. It was confirmed independently by multiple observatories using both optical and radio data. That means one of two things. Either 3i Atlas has a hidden reservoir of stored energy, something internal, buried deep within, or the object is converting solar energy with a level of efficiency that no natural body has ever demonstrated. Stored energy is the first explanation most researchers reach for. Perhaps the object has been carrying volatile ices deep beneath its surface for millions of years. Maybe the heating is finally reaching those layers. That could explain the sustained jetting, if enough pressurized material is being released all at once. But that raises its own problems. Sustaining jets for this long requires not just material, but a way to direct and control it. Outgassing should cause the body to wobble, it should destabilize rotation, it should be messy. But 3i Atlas is not wobbling, it's not destabilizing. Its brightness curve is smooth, its orientation is steady, and that leads to the second, more troubling possibility. Maybe the object is not simply absorbing sunlight. Maybe it's using it, not just passively heating up, but actively converting radiation into focused, directional energy. That idea belongs more to spacecraft than to comets. Solar sails, ion drives, thermal propulsion all rely on this kind of conversion, but 3i Atlas shows no panels, no obvious structure, just smooth surface features and collimated jets. So the energy question lingers. It doesn't scream, it doesn't demand, it just whispers. If this is natural, then why hasn't nature done it before? When faced with a system that appears to be producing more energy than it receives, the mind reaches for the simplest explanation. It must have started with energy already inside. That's the stored energy hypothesis. Maybe 3i Atlas is like a frozen pressure vessel. Maybe its long interstellar journey locked enormous reservoirs of chemical potential deep within its nucleus, pockets of volatile gas or exotic ices, compressed over eons waiting to be released. If sunlight finally reached those layers, perhaps it triggered a slow detonation, not destructive, but sustained. One that could power the persistent jets observed near Earth on December 19. It's an appealing theory, familiar. It preserves the idea that 3i Atlas is natural, just rare, not alien, not engineered, just different. But the closer you look, the harder that story is to believe. For stored energy to explain the jet activity, several assumptions must hold true. First, that the nucleus is large enough to hold vast internal reservoirs. Second, that those reservoirs remained sealed and undisturbed despite millions of years drifting through the galaxy. Third, that sunlight happened to trigger symmetrical venting from specific locations on the surface. And fourth, and most improbable, that this release could be sustained without destabilizing the object's orientation. That last point is crucial. Stored energy, once activated, is chaotic. It surges, it escapes unevenly, it drives cracks, rotation, and in comets, often violent fragmentation. But 3i Atlas shows none of those effects. Its rotation is smooth, its surface appears intact. The jets are not bursting through random fissures. They emerge from fixed coordinates, structured, controlled. This control is where the stored energy model begins to fall apart. Even if pressurized volatiles were buried deep within the comet, they would need channels, vent shafts to escape so precisely. Those channels would have to withstand thermal expansion, radiation bombardment, and rotational torque. Natural vents don't last that long. They erode, they clog, they shift. Yet the jets on 3i Atlas remain collimated, thin and coherent, across multiple observation cycles. That kind of consistency suggests maintenance, not accident. Then there's the question of balance. If energy is being released in such large quantities, why doesn't the object react more violently? The physics of Newtonian motion says that venting material in one direction should push the nucleus in the opposite direction. That force should cause drift, or at least visible acceleration. And it does, but not randomly. The movement of 3i Atlas aligns almost perfectly with the solar vector. The trajectory shift is smooth, not staggered. That's not how internal outgassing usually looks. It jitters, it forces rotational wobble. But here we see something that resembles propulsion, not just momentum loss. Stored energy might explain the presence of jets, but it does not explain their precision, it does not explain their direction, and it certainly does not explain the energy budget itself. When astronomers calculated the kinetic output of the material being ejected, mass times velocity, they found it exceeded the maximum solar input by a wide margin. If the energy were coming from inside, it would need to match that output across hours, even days. That requires a fuel source unlike anything found in standard cometry models. So scientists began asking harder questions. What if the object isn't just leaking? What if it's regulating? What if the energy flow is being managed not by randomness, but by rules we don't yet understand? Stored energy is comforting. It fits within the known universe. But the jets of 3I Atlas on December 19 didn't behave like entropy being released. They behaved like thrust being aimed. And that makes all the difference. On the morning of December 19, the position of 3I Atlas relative to the Sun was no mystery. Its heliocentric coordinates had been refined for weeks. It was inbound near its closest approach to Earth, with the Sun positioned off its left flank from Earth's vantage point. That configuration placed the solar vector, essentially the direct line between the object and the Sun, at a well-known angle. And it's here, along that invisible line, that the most unexpected feature began to emerge. The jets on 3I Atlas were not simply visible. They were oriented, and not just randomly sprayed into space like outgassing from a ruptured seam. They were tightly focused, structured, and, most critically, partially aligned with the solar vector itself. This is not something nature typically does. In standard comet behavior, the tail and jet features almost always orient opposite the Sun. Solar radiation pushes gas and dust away. Even heavier particles, which resist the solar wind, eventually curve into trailing arcs due to orbital motion. The physics are straightforward. Material moves from hot to cold, from light to shadow, from pressure to vacuum. You heat the sunward face of a nucleus, and material boils off. But it gets pushed back, scattered away from the Sun, not toward it. So when the brightest jet on 3I Atlas began trending toward the solar vector, rather than away from it, observers were skeptical. At first, some suspected a viewing artifact. Perhaps the jet merely appeared sunward from Earth's angle, but was in truth slightly offset in three-dimensional space. But that theory didn't hold. Images taken from independent observatories, some ground-based, some orbital, captured the same alignment, even when the object's position relative to Earth changed. The solar vector remained constant, and so did the jet. That consistency shattered the illusion theory. More surprising still was the realization that this wasn't a single errant vent. A secondary jet, smaller but still coherent, was also observed aligning nearly 180 degrees in the opposite direction, meaning it pointed away from the Sun along the same axis. In other words, both jets traced a line that connected directly through the nucleus and into the solar vector. The object was not just active, it was symmetrical. Natural comet behavior does not include bilateral alignment. And this leads to a deeper problem. If a jet is aimed toward the Sun, then by Newton's third law, the object should be pushed away. This is not speculation, it's propulsion. When mass is ejected in one direction, there is an equal and opposite reaction. It's how rockets work. And while comets often shift slightly from asymmetric outgassing, those shifts are irregular and noisy. They do not trace a curve. They do not sustain. But 3I Atlas did. Orbital refinements on December 19 showed a minor acceleration away from the Sun, consistent with thrust, not drift, and that thrust aligned with the observed jet geometry. At this point, some researchers began to use the word vectoring, not publicly, not in papers, but internally in the models and simulations they were now forced to run, because the physics demanded it. If the object was accelerating along the solar vector while simultaneously ejecting mass in the opposite direction, the implications were hard to ignore. The only remaining question was whether that alignment was intentional or just extraordinarily lucky. But luck runs out quickly in orbital mechanics, and this object wasn't deviating. It was adjusting. The solar vector is not something you follow by accident. By now, the object was no longer just a curiosity. It was behaving like a system. And when systems move, the question always returns to one man, Newton. Isaac Newton's laws of motion have governed orbital dynamics for centuries. Every satellite we've launched, every comet we've tracked, and every slingshot maneuver we've calculated rests on one simple truth. For every action, there is an equal and opposite reaction. It sounds like a philosophical idea, but it isn't. It's a law of physics, one that has never been broken. So when 3i Atlas began ejecting material in a direction partially aligned with the Sun, it became more than a visual anomaly. It became a test of momentum, because if something pushes, it must also be pushed. The narrow jets seen on the morning of December 19 weren't drifting clouds. They were fast-moving coherent plumes. Material was leaving the nucleus, and if Newton's law holds, then that same nucleus had to be reacting in the opposite direction. This is the cornerstone of propulsion. All spacecraft obey it. They burn fuel in one direction to move in another. They don't need to push against anything. They just need to eject mass. And if that mass is directed with precision, the resulting movement is equally precise. So the question is not whether 3i Atlas could be moving in response to its jets. The question is how much, and how smoothly. When astronomers ran the numbers, they found something strange. The object's velocity had shifted slightly. Not enough to be dangerous, but enough to notice. It had accelerated away from the Sun by a few meters per second. That's not an enormous amount, but it's measurable. More importantly, the direction of that acceleration matched the vector of the Sunward jet. This wasn't random. Most comets exhibit non-gravitational acceleration. It's a well-known phenomenon. As they heat up, they vent gas, and as gas escapes, it nudges the comet. But those nudges are messy. They're chaotic. They vary as the rotation of the body exposes different faces to the Sun, and because comets are irregular, the resulting movement is often wobbly, staggered, or difficult to model. That is not what happened here. The trajectory change in 3i Atlas was smooth. It was curved, and it was continuous. It followed a pattern that's easier to model with a propulsion equation than a fragmentation one. That's where Newton's second law enters. Force equals mass times acceleration. If you know the amount of material being ejected, and you know the velocity of that material, you can calculate the force being applied to the object. And if you know the mass of the object, you can predict how fast it should accelerate in response. Astronomers did the math, and the acceleration observed in 3i Atlas on December 19 matched the predictions, if the jets were sustained at high velocity in a sunward direction. In other words, the motion was not a mystery. It was expected by physics, but not by comet science, because comets don't eject mass like thrusters. They burst, flare, then fade. They wobble, they spiral, but they don't hold a vector. 3i Atlas was doing something different. It was behaving like an object that understood the consequences of its own momentum. That doesn't prove design, but it does prove coherence. And coherence, when paired with symmetry and precision, begins to resemble intent, even if unintentional. Newton doesn't care what the object is, he only cares what it does, and on that morning it behaved like a spacecraft. The laws had been respected, Newton was satisfied. But the universe wasn't done speaking. As 3i Atlas continued its approach toward Earth, what came next wasn't dramatic. It wasn't a violent outburst or a rapid spin. It was a whisper, a quiet deviation, a nudge that almost went unnoticed, until someone looked closer. On the morning of December 19, high-precision tracking arrays across both hemispheres picked up a change. It was not a drift in brightness, it was a drift in path. 3i Atlas was no longer following its exact projected course. When observatories compare a comet's orbit to its predicted path, they look for deviations that might indicate new forces at play, thermal expansion, gas outflow, even subtle gravitational tugs from nearby objects. All of these are accounted for in the models, and yet, even after compensating for all known factors, one thing remained unaccounted for. The object was veering, ever so slightly, off its originally predicted arc. Not away from Earth, but closer. It wasn't the kind of course correction that would trigger an alert at a defense agency. This wasn't an extinction-level vector. It was subtle, less than a fraction of a degree. But when you're dealing with interplanetary distances, a change that's small can shift a trajectory by thousands of kilometers over time, and that's exactly what was happening. At first, it was attributed to outgassing. But the observed plume from earlier, jetting toward the Sun, didn't explain this new vector. If anything, it should have pushed the object in the opposite direction. So scientists ran the simulations again. They input all known data, mass estimates, jet duration, solar pressure, tidal influences, and previous acceleration vectors. But the numbers didn't fit. Something was adjusting the trajectory in a way that mirrored, almost exactly, what a planned maneuver would look like if you were trying to arc around Earth rather than plummet directly into it. That phrasing, planned maneuver, sent chills through some of the analysis teams. To be clear, nobody was suggesting it had intent. But the mechanics of the drift mirrored something very specific, a low-energy gravity assist maneuver. It's a technique we use with our own spacecraft. When done correctly, you can slingshot around a planetary body and gain velocity or shift direction without using fuel. The key is timing. The approach must be aligned with the planet's own orbital momentum. Get it wrong, and you either miss the slingshot or enter an unstable orbit. But get it right, and you steal a little bit of motion from a moving world. 3i Atlas appeared to be setting up for exactly that. Its curve toward Earth was gentle, not steep, not suicidal, not the trajectory of an object out of control. It was precise. In fact, too precise to be random if driven only by outgassing, especially considering the rotational irregularities most comets exhibit. The mystery deepened, because now the alignment anomaly seen earlier, the Sunward jet, made more sense in context. That energy release may have been the initiator, a kind of correctional burn, and the drift that followed might have been the result. But here's where it became unnerving. The adjustment was continuing. Not just a one-time deflection, but a sustained, curving deviation that brought it into an even more accurate proximity with Earth's orbital plane. It looked like targeting. Again, not in the hostile sense, but in the navigational one. In thousands of simulations, only a handful of natural comets had ever shown this kind of long-range curvature, without being chaotic, without fragmenting, and without tumbling. Most lose cohesion, many break apart, almost none align. 3i Atlas was aligning, by accident, by design. The telescopes didn't care, they just recorded. But in the minds of many scientists watching the data feed in real time, one shared thought rose quietly to the surface. If this were a spacecraft, this is exactly what it would be doing. As the object traced its new curve, sunlight became more than an illumination. It became a narrator. In the early hours of December 19, the arc of 3i Atlas pulled slightly closer to Earth's orbital path. Not sharply, not violently. It was a graceful tilt, subtle to the eye, but enormous in implication. And with this new angle came a shift in how it reflected light. That's what most observatories picked up first. Not the trajectory, not the chemistry, but the shift in how sunlight danced across its body. For a few hours, 3i Atlas began to shine with a more stable brightness profile, as if the spin had settled, as if it had aligned just enough to reduce the erratic flickers seen in previous days. This new alignment allowed Earth-based telescopes to get some of their clearest light readings to date, and what they revealed wasn't uniform. Instead of a smooth, consistent glow, what you'd expect from a symmetrical nucleus or a chaotic dust cloud, there were repeating light patterns, pulses. Some researchers dismissed it as surface rotation. After all, many comets tumble. But others noticed something more organized. The brightness pulses weren't just timed, they were spatially consistent. They traced along the same radial path, indicating a repeating geometry, almost like panels or surfaces that only glinted when perfectly aligned with the sun. This wasn't the flicker of an icy rock. It was rhythm. But even beyond the light pattern, the timing of this alignment raised questions. Because if the object was now entering the most visible part of its arc, fully lit from the Earth's perspective, this was the moment to study it with every available instrument. So they did. Infrared telescopes noticed something unexpected. There was a hot zone, not facing the sun but slightly offset. This wasn't explained by solar radiation alone. Instead, it hinted at an internal heat mechanism, or perhaps residual thermal energy from earlier jet activity. Whatever it was, it defied the cooling curve expected at this distance. Spectrographic scans revealed another subtle shift. A new spectral line appeared, just faintly, in the yellow-orange band. It didn't match standard signatures for sodium or iron alone. It hinted at an unusual compound, possibly sulfur-based, possibly synthetic, but it was too faint to lock down. Still, it wasn't there 3 days earlier. Now it was. And here's where the arc became eerie. Because every major interstellar object previously catalogued, Oumuamua, Borisov, even early long-period comets, showed unpredictable behavior as they approached the sun. Spin changes, brightness surges, fragmentation. 3i Atlas did the opposite. It stabilized. Its tail became cleaner, its motion became smoother, its spin, while still irregular, seemed to reach a plateau. For those monitoring closely, it felt choreographed, like something had finished adjusting and was now entering its primary path, a sunlit trajectory that pointed, not directly at Earth, but tangentially close enough to raise collective eyebrows. And just as this alignment made 3i Atlas more visible to Earth, it also raised another realization: we were now visible to it, fully illuminated, reflecting sunlight back toward its sensors, if it had any. In purely optical terms, we were now standing in the spotlight. If this were natural, that wouldn't matter. But if this were artificial, if anything inside that object could perceive, it would now have a perfect view. The thought was unsettling, not because of what we knew, but because of what the light was starting to reveal. We were entering the clearest phase yet, and the arc wasn't just physical. It was symbolic, a curve that pulled 3i Atlas toward the truth, toward exposure, toward the edge of our atmosphere's reach, a radiant limb of sunlight tracing the story of something that still refused to make sense. And this alignment wasn't random. It was deliberate, measured, like a theatre curtain being pulled back at just the right moment. And what it would reveal next would depend on the shadows we were about to see. By the time 3i Atlas crossed into full visual clarity from Earth's perspective, most observatories had trained every available sensor on its tail, but what they found was not the simple structure of ice particles and gas expanding in space. The dust itself, normally passive, chaotic, and fading, was doing something strange. It was staying organized. In standard comet behavior, once material erupts from the surface, whether through solar heating or structural breakdown, it tends to disperse rapidly. Even with large outgassing events, particles fan out, obeying the laws of thermal motion and radiation, pressure. But the dust cloud trailing 3i Atlas wasn't behaving that way. At first glance, it looked conventional, a tapering formation stretching thousands of kilometers, speckled with fine particulate and curling, like the tail of a typical sun-warmed comet. But when high-resolution polarimetric scans were processed, the pattern broke from expectation. Instead of a smooth gradient of particles diffusing outward, there were filamentary structures. Not physical threads, no cables, no beams, but electromagnetic stratifications. Zones where particles seemed to align, held, as if organized by a magnetic scaffolding that shouldn't exist. Some researchers propose static charge differentials across the tail, a result of high-speed ion collisions or charged jets activating asymmetric fields. That might explain temporary lanes, but not persistent ones. Not these symmetrical ripples that held their shape hour after hour. And this wasn't the only anomaly. Under ultraviolet inspection, parts of the dust plume emitted with unexpected consistency, not in brightness, but in wavelength. A narrow band glow suggested the presence of complex carbon chains, polycyclic aromatic hydrocarbons, commonly associated with combustion processes and certain laboratory synthesis reactions. You can find them in meteorites. You can also find them in exhaust, and there was too much of it. Not scattered fragments or background contamination. It was centralized, originating from one part of the object's surface and maintained in uniform concentration, something difficult to explain by natural erosion alone. That's when teams from the Atacama Desert facility picked up something even stranger. As the dust passed through solar crosslight, where Earth could observe it edge on, tiny shadows began to form inside the tail. That's not normal. In most comets, particles are too small and diffuse to cast visible internal shadows. But 3i Atlas's dust wasn't just particulate, it was clumping. Not merging into new rocks or coalescing into meteoroids, but clustering, aggregating in slow motion, resisting spread. Like particles were seeking cohesion, not dispersion. This opened the door to a rare hypothesis: self-organizing matter. In the vacuum of space, certain nanoscale particles, especially under strong electromagnetic influence, can align into wave-like structures. We've seen this in controlled environments. Never on this scale. If 3i Atlas was generating its own local field, electromagnetic, electrostatic, or something more exotic, it might explain the strange scaffolding holding these formations together. But the implications would be immense. It would mean this isn't just matter moving through space, it's matter responding to design. That's not to say artificial, at least not conclusively. Nature has its own blueprints: plasma filaments in deep space, spiral galaxies, the ordered chaos of Jupiter's storms, but here, within a structure already showing anomalies in trajectory, reflection, and heat signatures. Organized dust was a signal of intent. Even skeptics had to pause, because the one thing you expect from a tail is entropy. What we were seeing was order. Some called it a glitch in the data. Others said we were witnessing a rare moment of structured decay. But for those watching live feeds from the James Webb interface, one thing was clear. The dust wasn't just leaving the object, it was circling back. It was bending in formations too stable for randomness, and every spiral, every arc, pointed sunward, as if 3i Atlas was drawing something behind it, like ink from a pen, like a message, waiting to be read. In every comet we've observed over the last century, there's a rule so consistent it's become foundational. The tail always points away from the sun, not because of gravity, but because of the solar wind, streams of charged particles that bombard any object in the inner solar system and blow the lighter gases and dust into a radiant arc that stretches away from the star. But 3i Atlas, it didn't obey the rule. When it came into solar alignment early on the morning of December 19th, the tail didn't simply fan out in the expected direction. Instead, it split. One section drifting out behind, but another one curling forward, arcing gently toward the sun itself. It was subtle at first, a ripple, a deviation in the outer plasma sheath that many wrote off as turbulence in the solar wind. But as Earth's angle shifted and new observatories joined the imaging array, the anomaly became undeniable. There was a second tail, and it was pointing the wrong way. This sunward-facing component wasn't made of dust. It was thin, almost imperceptible unless viewed in extreme ultraviolet. But when captured, it glowed. Not in the dispersed shimmer of gas, but in a narrow, focused spectrum. A beam rather than a trail. Narrow, controlled. That term, controlled, became the subject of heated debate. In natural systems, even the strongest cometary jets don't maintain directional focus for long. Outgassing is chaotic, driven by surface heating, rotational spin, and fragmenting crust. But this structure didn't fluctuate. It pulsed, like a heartbeat, faint but rhythmic. The cadence was regular. Every few minutes a burst, each one slightly more intense than the last. It wasn't random, and it wasn't symmetrical either. The pulses travelled in one direction, toward the sun, suggesting not just ejection, but targeting. Some theorized it was a reaction, an unstable feedback loop between the comet's nucleus and the sun's electromagnetic field. Others proposed a more unnerving idea: active orientation. That 3i Atlas, as it spun, was releasing particles not away from the sun, but toward it, intentionally. The implications were staggering. If this object, already displaying tail anomalies, organized dust behavior, and trajectory corrections, was now expelling material, in a directed sunward beam, it might suggest solar interaction on a level we hadn't seen before. Not collision, not fusion, but communication. And just as this theory was gaining momentum, something even stranger happened. The light beam changed color, not visibly, but spectrally. Instruments detected a shift in the emission line, a narrowing of wavelength that didn't match any simple ionization of hydrogen or carbon. It hinted at a compound emission, something layered, as if the particles being ejected were modulated, designed to carry structured information. A message, some whispered. Others called it a natural artifact, like a CD thrown into the air, catching sunlight in a pattern that only looks deliberate. But the metaphor struck deep. Because 3i Atlas wasn't just behaving like a comet anymore, it was behaving like a system, with outputs, with rhythm, with directionality. And this forward-facing tail, this sunward anomaly, was its signal. And in a way it made sense. If you were trying to send a signal anywhere in the solar system, the sun would be your best medium. It touches everything. Its particles reach every planet. Its magnetic field bends around every object. It is the one constant communicator across the vastness of space. And 3i Atlas, it was writing into that current, carving lines into solar breath, emitting not just dust, but code. We couldn't read it, not yet. But as the comet crept closer, the tail grew brighter, more focused. The signal, if that's what it was, became harder to ignore. It was as if 3i Atlas wasn't just surviving the sun, it was speaking to it, and the solar wind, our old reliable narrator of tail direction, was no longer in control. By mid-morning on December 19th, a growing number of telescopes, not just in orbit, but also Earth-based facilities in Chile, Hawaii, and even Antarctica, were all triangulating their focus on one strange pattern, pulsing from within the nucleus of 3i Atlas. To the naked eye, 3i Atlas still looked like a glowing fragment of space dust bathed in sunlight. But under the scrutiny of magnetometric arrays and deep penetrating radio spectrometry, the core of the object was telling a very different story. It was alive with rhythm. Not biological life, of course, but motion. A kind of internal vibration. A heartbeat. Something deep beneath the surface was sending out consistent pulses that couldn't be explained by thermal cracking, crustal fragmentation, or any of the usual natural processes we observe in icy interstellar visitors. This was not the random breaking apart of frozen rock. It was timed, repeating, stable. And when researchers adjusted the instruments to amplify subsurface echoes, the result was stunning. The signal bounced. Instead of scattering as it should through a porous, cracked interior, as is typical for comets, this signal rebounded cleanly off multiple internal layers that appeared smooth, structured, possibly even curved. The pulse did not originate from the surface. It radiated outward from deep within the center of the object. And it wasn't just one pulse. There were two, each staggered by just under a second. A dual rhythm, a syncopated beat echoing through what now looked less like a loose rubble pile and more like a structured interior. And then came the most unsettling discovery. As the sun's energy increased and the outer shell of 3i Atlas became more active, venting gas, shedding dust, glowing with unusual intensity, the pulse did not weaken or fluctuate. It remained steady. It was not reacting to the environment. It was operating on its own schedule, like a beacon. Even more disturbing, the pulse was not random white noise. Audio engineers and data analysts from outside the astronomy community were invited to analyze the patterns. Some claimed to find modulation, tiny variations in the intensity of each beat that followed predictable steps. Others dismissed it as audio pareidolia, the tendency to find order in noise. But there was one undeniable fact. No other known comet in recorded history has produced such a coherent internal signal, especially while under this much solar stress. And if the object had fractured before, or if the interior were collapsing under tidal forces, we would expect the rhythm to shatter, degrade, or distort. Instead, it became clearer, more refined. The pulse, once a whisper beneath layers of ice, was now something else. Some called it a signature, others a countdown. But one group, studying the rotational dynamics of the object, noticed something extraordinary. With every pulse, the rotation of the comet adjusted ever so slightly. Not randomly, but toward the same axis. It was as if the interior signal was interacting with the object's spin, stabilizing it, aligning it. That alignment was toward the sun, and slowly, piece by piece, the comet's chaotic tumble shifted. The spin smoothed, the jets became balanced, the tail narrowed, and the signal from within remained steady. Whatever was inside 3i Atlas, whether geological, artificial, or something stranger, was not being destroyed by proximity to the sun. It was awakening, and Earth, watching from just one step away in the cosmic spiral, could do nothing but listen as the beat beneath the ice grew louder. Just after midday on December 19th, while most of the world remained unaware of what was unfolding, a narrow-band transmission anomaly was quietly logged by the ESA's solar orbiter as it passed between Earth and the Sun. At first, the signal appeared to be nothing more than ordinary electromagnetic interference, something that happens often when solar radiation interacts with high-gain antennas. But this wasn't solar noise. This signal came with a delay, a stagger, a momentary bounce not from Earth and not from the orbiter itself, but from the region between the two, a region where, on any other day, there would be only the void, black vacuum, and nothing more, except today that space held 3i Atlas. Engineers on the mission replayed the sequence. What they saw was deeply puzzling. The radio ping initially intended to map solar particle density had bounced back twice, once from the expected solar corona, and once again fainter, delayed, but with a signature that did not match the solar wind. It came back from a structured interface, something partially reflective with a measurable angle of deflection. But it wasn't metal, it wasn't ice, it was something in between. Spectral analysis of the returning echo showed unusual attenuation in the far ultraviolet band. Normally, when sunlight bounces off a comet's tail or coma, the returning light is diffuse, scattered across the electromagnetic spectrum due to the chaotic nature of the dust cloud. This was the opposite. The returning signal was tight, refined, and, most curiously, it was modulated. Not in a way that suggested communication, but in a way that suggested behavior, like a feedback loop. The comet wasn't just passively reflecting energy, it was interacting with it, processing it. That behavior had a visible consequence. High-resolution time-lapse imaging from the Daniel K. Inouye Solar Telescope in Hawaii revealed a subtle flicker across the tail of 3I Atlas in the moments following the echo. Almost like the shimmering of a mirage across hot asphalt. But it wasn't a trick of light. The tail was reacting. The shape of the gas column changed, curling inward, not from solar wind pressure, but from something emanating within the object itself. At the same moment, the jets on the sunward side surged briefly, before stabilizing into an even tighter fan. That surge coincided perfectly with the time the secondary echo had been received. The implication was stunning. Whatever was inside the object was not only emitting pulses, it appeared to be absorbing and adjusting to external radiation. In other words, it was responding to the sun. That was the moment scientists began using a new term. No longer just interstellar object, not just comet. They began calling it a solar reactive structure. And with that shift in terminology came a shift in tone across observatories. The data wasn't being interpreted through the lens of classical comet science anymore. Now it was being scrutinized with tools designed to study satellites, probes, and powered objects. Because something inside 3I Atlas was behaving like it understood the sun, not just as a source of energy, but as a variable, a signal, a control. Some even speculated that the alignment anomaly, the precise tilt toward the sun, wasn't just a random gravitational effect, it may have been intentional, a reorientation for optimal exposure, like a flower turning toward the light, or a sensor being positioned for input. And as scientists recalibrated instruments to watch for additional echoes, one chilling thought began to form in their minds. What if this wasn't a response? What if this was a call, and the sun had just answered? By late afternoon on December 19th, researchers at the Subaru telescope on Mauna Kea released a series of filtered images that immediately drew sharp attention from every observatory already focused on 3I Atlas. The images were not ordinary wide-angle captures of the tail. Instead, they were the result of polarized light filtering, used to examine how light scatters off fine particles, often revealing structure invisible to the naked eye. When the data was compiled, layered, and enhanced, it revealed something no one expected to find. The tail wasn't uniform, it wasn't chaotic, and it wasn't even random. Instead, the material ejected from 3I Atlas over the past 36 hours had begun to form a clear, repeating geometric pattern, a wave-like structure embedded into the curvature of the tail itself. At first glance, it resembled ripples in a pond. But the spacing between the ripples was too exact, too synchronized, almost like the grooves on a vinyl record, measured, consistent, encoded. Researchers examined the pattern further using Fourier analysis, a technique typically reserved for processing audio signals or deciphering light curves in variable stars. To their astonishment, the structure held a stable frequency, not random jets, not chaotic dust dispersal, but rhythmic bursts, pulses of material being released from within 3I Atlas at nearly perfect intervals. One astrophysicist, after reviewing the data, quietly remarked, "This doesn't look like nature, this looks like design." What made the situation even more curious was where in the tail the geometry emerged. Most comets release material from their sunward side, where heat causes surface ices to sublimate. The released gases push away from the sun, forming both the dust tail and the ion tail. But in the case of 3I Atlas, the repeating pattern was not in the central spine of the tail. It was embedded off-axis, angled slightly, and only visible when the object was viewed from a specific plane. That meant the pulses were directional, controlled, not merely reactive to solar radiation. Further simulation models run by the Swedish Institute of Space Physics suggested the pulses may be modulated in such a way as to form constructive interference patterns, where overlapping waves amplify one another. In the realm of fluid dynamics and magnetohydrodynamics, this could suggest 3I Atlas was not only emitting material, but doing so in a way that reinforced or shaped the resulting flow of particles. This again hinted at behaviour, not accident. What exactly the geometric pattern meant, no one could say for certain. Some theorized it could be related to internal rotation, like a spinning core emitting bursts as it turns. Others believed it might be a form of data encoding, a log, a record. But one hypothesis stood out from the rest. A group of astrophysicists from the European Southern Observatory proposed that the repeating geometry may be a navigation system, a means of maintaining course using radiative pressure. In other words, the pulses weren't just random, each might serve as a micro-adjustment, correcting the object's flight path in response to gravitational forces or solar interference. It would explain why the alignment of 3I Atlas had remained so shockingly precise, even as it passed through complex fields of solar magnetism. The Sunward alignment anomaly wasn't just an effect, it could be the goal, and the geometry in the tail was the mechanism. At that moment, the language used to describe 3I Atlas changed once again. The term interstellar visitor began to fade. The term natural body lost traction, because what they were seeing in the tail was a pattern of control. And when nature begins to behave with control, we're forced to ask the question, who or what is in control of it? As 3I Atlas passed through its most Earth-facing orientation, on the morning of December 19th, a final burst of observational data poured in from the European Space Agency's solar orbiter. This probe, trailing behind Earth, in a slightly offset orbit, captured something the ground-based telescopes couldn't: thermal readings across multiple spectrums, including mid-infrared. Infrared scans are one of the most reliable tools in astrophysics. They don't just show what something looks like, they show how it breathes, how it radiates, how it changes temperature as it reacts to light, shadow, heat, or internal processes. And what they found in the thermal spectrum of 3I Atlas simply didn't make sense. Normally, a comet or interstellar object approaching a star shows predictable heating profiles. The sunward side gradually warms as it absorbs solar radiation. The core remains colder for longer. Ejector materials, gases, dust, volatile compounds flare in brightness and gradually thin out. But the heat signature of 3I Atlas was wildly asymmetrical. Not only was the tail hotter than expected, it was hotter in isolated bands, distributed like internal veins along the central spine of the tail, almost like a set of heat channels. But that wasn't the strangest part. The body itself, what scientists believed was the nucleus, showed almost no consistent heating at all. It remained stubbornly cool. So cool, in fact, that it couldn't possibly be the source of the ejector unless a separate internal system was regulating thermal flow. It was like watching a machine radiate only from its exhaust vents, while the core remained untouched. It defied every expectation of solar interaction. One theory began to gain traction, though it was treated cautiously. Some scientists began comparing the pattern to thermal shielding, a concept used in both aerospace and materials science. The idea is simple: reflect or deflect incoming heat to protect internal systems. Spacecraft use layered shielding, certain animals use pigmentation or behavior. But for a comet to exhibit this kind of behavior, that was something entirely different. The math was undeniable. 3I Atlas was not passively absorbing solar heat like a natural object, it was managing it. Researchers from the Kavli Institute for Astrophysics simulated the surface reaction of various ices and regoliths under high-energy solar exposure. None matched the observed heat profile. Even layered silicates or carbon-rich surfaces would show a gradual heating curve. Instead, 3I Atlas appeared to maintain a flat line in thermal activity across its surface, except in moments when new jets erupted. And when they did, they followed no solar rhythm, they followed a pulse. Every 27 minutes a small jet ignited, expelled material into space, and then went dark again. It was rhythmic, intentional, controlled. That's when one physicist in Geneva made a quiet observation. They weren't looking at thermal decay, they were watching a reactor cycle. This wasn't heat leaking out, it was pressure release, which begged the question, what was building that pressure inside? Could it be tidal forces from the sun, internal core instability, or something more engineered? The more they examined the data, the less it looked like a chaotic melting process, and the more it resembled a system under regulation, a system that maintained internal equilibrium by precisely timed ejections of heat and material, without compromising its shell, and this brought them to a deeply uncomfortable conclusion. Natural objects don't regulate heat like this. They don't hide their warmth. They don't synchronize their thermal emissions like clockwork, and they don't actively keep themselves cold while emitting jets of energy across space. In the entire history of solar system observation, nothing, absolutely nothing, had exhibited this kind of behavior. At that moment, the idea of 3I Atlas being a dormant comet, or even a tumbling interstellar rock, collapsed under the weight of its own emissions. Because when something manages its own heat, it's no longer passive, it's operational, and something operational is no longer alone in the category of natural. While the world's largest observatories were busy decoding the inexplicable heat behavior of 3I Atlas, something far subtler was unfolding just below the radar, within the growing community of amateur astronomers. Armed with backyard telescopes, open-source imaging tools, and boundless curiosity, this network had quietly become a crucial global grid of observation, and what they began noticing on December 19th would send shockwaves back up the professional ladder. It started with a series of posts on a small astronomy forum based in Italy. A user named Lunaris Delta, a retired optical engineer, had been live tracking 3I Atlas for several weeks. His setup was modest: a 12-inch Schmidt-Cassegrain telescope, a high-sensitivity CCD camera, and a software stack built to auto-stack exposures over time. But on that particular night, as he stitched together frames from a 3-hour observation run, something stood out. It wasn't what he saw in the comet's tail, it was what he didn't see in its shadow. Every known comet reflects light based on the angle of the sun, Earth, and the object's rotation. As a result, they cast what is known as a shadow line, a gradient between the lit hemisphere and the dark one. This line moves predictably, like the Terminator on the moon, as the body rotates and tumbles. But 3I Atlas showed no such gradient. Instead, the entire visible face appeared evenly lit from the front, not just from the solar side, but seemingly from multiple angles. Even stranger, the outline of the nucleus had softened, not due to blur, but due to a faint glow that began wrapping around the dark side. The amateur community dubbed it the halo effect, and soon, dozens of other independent observers began confirming the same result, from Poland, Argentina, New Zealand, and even rural Montana. They compared their images, overlaid timestamps, and found an eerie uniformity. The shadow line of 3I Atlas had stopped moving, and then, more chillingly, it had vanished altogether. For a celestial object this close to the sun, under extreme illumination and angular variation, such a phenomenon had no precedent. Some speculated it was the result of light scattering through a dense coma. Others suggested electromagnetic interactions with solar wind might be warping the visible structure of the tail. But those explanations fell apart under scrutiny, because this wasn't just a change in tail structure or coma diffusion. This was light wrapping around an object that shouldn't allow it, an object with no known mechanism to emit or reflect light from its dark side, unless it was being illuminated from within. Some tried to simulate this in 3D modelling engines, attempting to recreate the lighting from all known sources: solar, terrestrial backscatter, even lunar reflectivity. None of them matched the real images being uploaded every hour. A physicist in Brazil uploaded a composite that captured it perfectly: a nucleus bathed in forward light, with a soft ring of glow encircling the back edge. It resembled the type of contour you'd expect from a translucent or backlit object. Not a rock, not an icy fragment, but something porous or semi-hollow. When the data reached the Minor Planet Center, several researchers began cross-checking it with archived images from early December, and sure enough, the shadow line had been shifting, gradually stabilizing, until this moment of perfect alignment. But alignment with what? The sun's position hadn't changed enough to explain it. The Earth's angle of view couldn't account for total shadow disappearance. And comets don't suddenly begin glowing from the inside, unless they were designed to. The implications were too enormous to state publicly, But among the encrypted chats of observatory scientists and space agencies, one theory kept surfacing. What they were witnessing wasn't a natural reaction to light. It was a form of positional signaling, a maneuver, a slow, deliberate orientation toward the sun, not for warmth, but perhaps for communication. What began as a vanishing shadow line quickly evolved into something far stranger, something that experts across the solar observation community would later call the sunlight vector lock. Initially, it seemed like a natural evolution. If the shadow had vanished due to some light diffusing property within the coma, perhaps the angle of solar incidence had simply reached a perfect balance. But this assumption was short-lived, because 3I Atlas didn't just continue to glow from every angle. It began orienting itself in ways that no known object of its shape, composition, or trajectory should have been able to do. The shift was so subtle, so slow, that it took several hours of high-frame captures and composite analysis to detect it. But once seen, it was undeniable. The nucleus had begun maintaining a constant sun-facing orientation, a kind of solar lock usually seen in spacecraft with attitude control systems. This wasn't passive tumbling. It wasn't the gentle roll of an icy fragment being spun by outgassing jets. This was precise. The nucleus wasn't just facing the sun, it was tracking it. From multiple observatories, including Mauna Kea in Hawaii and Gran Telescopio Canarias in Spain, researchers began compiling high-resolution visual data from before and after perihelion. They noticed that the anti-tail, typically erratic and sprawling in most comets, had streamlined into a tight, narrow shaft of light, as if it were being pinned backward by some internal stabilizing force. This stabilization ran counter to all expectations. At this stage in a comet's journey, having passed its closest point to the sun, and now inbound toward Earth, the rotation should have been chaotic. Radiation pressure, gravity tides, and jet eruptions from the surface typically introduce tumbling or fragmentation. But 3I Atlas wasn't just avoiding chaos, it was acting as if it had corrective control. Every time solar wind pressure fluctuated, the body tilted to compensate, subtly but with measurable precision. The brightest side remained pointed toward the sun like a sunflower seeking light, even as space weather changed and photon momentum fluctuated. NASA analysts, reviewing thermal telemetry and reflected spectra, noticed a consistency in the surface brightness of the forward face. It didn't matter where Earth moved, or how the object drifted through different heliocentric angles. The same area remained facing the solar vector, emitting a steady radiative signature. It was as if 3I Atlas had locked onto the sun not merely for orientation, but for interaction. The idea seemed unthinkable. Comets don't lock on to anything. They are passive. Travellers, refugees from the Oort cloud or Kuiper belt dragged in by gravity, flung by momentum. They don't exhibit solar targeting behaviour, but here was the data. Dozens of instruments from independent agencies confirming it. The alignment was too perfect to be accidental. The vector never wavered, and as it moved closer to Earth, its positioning became even more fixed, like it was staring directly into the sun. Several hypotheses were floated in closed scientific channels. Some argued that a massive internal cavity was acting like a gyroscope, stabilizing the body via conservation of angular momentum. Others proposed that differential mass ejections, small jets on precise axes, were being fired to maintain balance. But both of these required a degree of internal structure and feedback control that no natural object had ever exhibited. There was no random spin, no solar drift, no evidence of the chaotic wobble that defines most post-perihelion comets. This was an object with intentional alignment, as if it wasn't just passing through the inner solar system, but trying to engage with it. And if it was trying to engage with the sun by maintaining that locked vector, then the next question was simple. What happens when it reaches Earth with that same face? What exactly is it pointing at, now? As 3I Atlas continued maintaining its impossible alignment with the sun, something else began emerging. Something invisible at first, but increasingly undeniable. Across several observation stations equipped with magnetoplasma instruments and heliophysics, grade interferometers, a new type of data fluctuation began to ripple through the streams. It didn't look like a traditional electromagnetic wave. It wasn't radio noise, solar wind turbulence, or cosmic background anomalies. It wasn't even tied directly to solar flare activity, which had remained relatively calm. Instead, it appeared as a distortion in phase alignment. tiny but measurable deviations in how local field lines were being read across multiple instruments. Initially dismissed as equipment drift or routine atmospheric interference, these anomalies became more pronounced as one common factor emerged: proximity to the line of sight with 3i Atlas. The distortion only occurred when instruments were trained within a certain arc of angular exposure to the object. Outside that range, signal integrity returned to normal. Inside it, interference became pronounced, even in frequency bands that should not have been impacted by cometary mass or ion tails. This was not a typical comet tail ionization artifact. This was something more spatial, something structural. Experts reviewing the data coined the term non-gravitational field distortion, because the anomalies weren't related to Newtonian mass displacement. The object wasn't bending light like a gravity well, it was bending measurements. Specifically, it was distorting field coherence, subtle patterns in how solar particles behaved when passing through that region of space. When solar neutrinos were measured, their paths showed no deflection, but ionized particles flowing along the Parker spiral magnetic lines began veering ever so slightly. This suggested something more profound. The space around 3i Atlas was being manipulated, not by mass, but by some active or reactive presence. The discovery prompted a rush of new instrument calibrations. ESA's solar orbiter adjusted its gyroscopic readings. NASA's Wind and ACE satellites were ordered to increase particle sampling in overlapping trajectories. Even the Chinese Chang'e network of Earth-Moon Lagrange sensors registered unusual delays in signal bounce-backs when aligned through the corridor now occupied by the object. It was becoming harder to dismiss. One analysis from a Stanford solar physics team likened the effect to a form of localized wave drag, a kind of wake in the solar plasma not caused by thrust, but by disruption of normal field harmonics. In other words, 3i Atlas wasn't just disturbing the space it occupied, it was reshaping how space responded to energy around it. To some, this was still a stretch. Comets outgas, they flare, they twist in solar winds. But even then, they don't affect magnetic alignment at a distance of millions of kilometers from their nucleus, and they certainly don't create predictable zones of particle distortion that move in phase with their core. And yet here it was. The data, repeating daily, confirmed by over a dozen sensors across multiple continents and orbits. The object was maintaining a zone of influence that seemed to stretch far beyond its physical size or mass signature. This revelation rekindled a controversial theory that had been circulating quietly since the Sunward alignment anomaly began. The idea that 3i Atlas was not simply reacting to solar physics, but perhaps generating a field of its own, one that could subtly manipulate local energy densities, plasma particle trajectories, or even feedback waveforms that affected observational measurements. In simpler terms, it was bending space behavior, not just space itself. That would place it in a category far beyond natural comets, a category usually reserved for engineered structures, gravitational wave experiments, or worse, unknowns. As Earth's orbit closed the distance, these field anomalies were no longer distant curiosities. They were becoming part of the immediate heliospheric environment. And something about the way they moved, the way they tightened, hinted that we were now inside their reach. For most comets, the behavior of their tail is predictable. Solar radiation pressure and the solar wind force the outgassed particles away from the sun, forming a long, luminous trail that always points in the opposite direction of our star. It's a ballet of charged particles, radiation, and gravity, something physics textbooks have explained for decades. But 3i Atlas didn't read the same books. As December 19th dawned, Earth-based observatories across the Pacific Rim and Europe started picking up something that at first seemed like a data glitch. In updated imagery of 3i Atlas taken by both ground-based scopes and near-orbit satellites, the object's tail didn't behave the way it was supposed to. Instead of trailing neatly away from the sun like a textbook example of solar wind behavior, the tail of 3i Atlas appeared increasingly angled, not away from the sun but slightly toward Earth. At first, this deflection was subtle, a few degrees, then more, until, by midday UTC, the tail exhibited an anomalous curvature, a kind of fluid-like motion that didn't match the forces acting on it. Scientists expected two possible tail structures, a dust tail that curves slightly due to inertia, and an ion tail that points directly away from the sun, pushed straight by the solar wind. But what they observed was something else entirely. The ion stream had twisted, curling and warping, then slowly aligning with Earth's orbital path. Not as a result of Earth's gravity, which wouldn't affect such tenuous particles over these distances, but as if the particles themselves were responding to something far more specific, as if the tail was being guided. Theories began forming rapidly. Was this a product of electromagnetic steering? Perhaps a natural field resonance caused by Earth's magnetic field? That would have required an impossible level of synchronicity. Earth's magnetosphere doesn't stretch that far, and even if it did, the tail wouldn't have the structural rigidity to follow a magnetic guide rail. The most disturbing possibility was also the most unspoken. What if 3I Atlas had emitted this tail not as a natural consequence of sublimation, but as deliberate directionality? What if the tail wasn't just pointing toward Earth? What if it was targeting it? This theory gained traction when ESA's plasma analyzer onboard solar orbiter detected a unique chemical marker in the tail's emissions. Normally, cometary tails carry signatures of ionized water, carbon monoxide, or cyanide gas, but this stream bore a distinct and repeating spike in helium-3, a rare isotope typically associated with solar fusion or engineered particle environments. This wasn't just a thermal outgassing of ice, this was directional, layered, and patterned. As the tail bent toward Earth, a series of low-frequency radio pulses were detected coming from the region of the tail's edge, barely above background noise, but consistent across 3 detection arrays. Each signal was followed by a slight increase in the tail's motion toward Earth's orbital path. That's when observers at the Allen Telescope Array began recording faint harmonics, vibrations in the electromagnetic band that didn't correspond to any known natural cosmic source. These weren't random. They appeared in cycles, with amplitude shifts precisely matching the object's trajectory changes. In simple terms, 3I Atlas was broadcasting something, while pointing its tail directly at Earth. The concern wasn't impact, it was exposure. What would happen if Earth passed through the core of that tail? Would the unusual particles, chemical isotopes, or harmonic pulses affect our ionosphere? Would satellites be at risk? Could this stream, if energized or structured, interact with Earth's magnetic field in ways we don't yet understand? In normal circumstances, a comet tail was beautiful, harmless, but in this case it felt too aimed, too organized, and it left experts quietly asking the question no one wanted to answer aloud. If this tail wasn't just gas, what else was in it? At first glance, the jets erupting from 3I Atlas might have seemed ordinary, blasts of gas and dust propelled by solar heating, creating visible trails as the comet rotated. But that illusion didn't last long. These weren't the kind of jets that appear randomly across a surface and fade with time. These jets moved, and not just with the spin of the comet, they turned. Every hour on the 19th of December, from multiple Earth-based observatories and spaceborne lenses, something began to emerge with startling clarity. A jet that had previously been erupting perpendicular to the core axis began to pivot, not with the rotation of the nucleus, but seemingly in deliberate redirection. It adjusted its outflow angle by nearly 30 degrees over the span of 4 hours. That was not a thermal response. That was something else entirely. At Mauna Kea, researchers reviewing spectroscopic data noticed a subtle shift in the wavelength of emissions from Jet 7, the strongest outflow on the western limb of 3I Atlas. The spectral lines were not only consistent with high-velocity water vapor and carbon monoxide, but also showed modulated intensity, rising and falling in near-regular pulses, and each pulse matched the timing of the tail's reorientation described earlier. In normal comets, jets are eruptions of gas and dust triggered when sunlight heats surface ice. They tend to occur near fissures or weak points on the nucleus, and they stay in place no matter how the comet turns. But 3I Atlas didn't follow those rules. This wasn't a sporadic geyser. This was a controlled vent. One by one, other jets began to demonstrate similar behavior. Their emission angles shifted, not randomly, but in coordinated arcs. Some slowed their output, others strengthened, and 2 jets even seemed to shut down completely before new ones appeared near the opposite pole. Across the observational community, radio silence turned to hushed disbelief, because what they were seeing didn't belong in any natural model. It belonged in propulsion. There was no escaping the comparison. It was as if 3i Atlas had reached a certain distance from Earth, and rather than simply coasting in its orbit, had begun to fine-tune its motion, steering, pivoting, course-correcting, using its own jets. But that's not how comets work. Unless, of course, it's not just a comet. At the European Southern Observatory, one analyst quietly noted a repeating time signature in the onset of each jet rotation. The interval was precisely 88 minutes, almost matching the orbital period of several low-Earth orbit satellites. It was as if the object had synced its jet firings with an external timing source, but no signals were being sent to 3i Atlas, at least none from Earth. The only known radio burst that coincided with the jet alignment came from deep space, background noise from Sagittarius A, the galactic center. Yet, somehow, the moment of peak alignment with Earth's orbital plane also matched the strongest observed thrust vector from the object's primary jet. The scientific community was split. Some insisted that what we were seeing was a rare form of dynamic outgassing, an ultra-reactive cometary surface combined with asymmetric heating from rotational wobble. But others saw a pattern far too organized to be natural. What if this wasn't just a course correction? What if it was positioning, not to avoid Earth, but to prepare? For what? No one could say for certain. But the jets weren't slowing. They were locking into rhythm, and the closer the object came to Earth, the more precise those jet alignments became, as if 3i Atlas was doing the unthinkable, stabilizing. No longer a tumbling object in space, but something aiming, something preparing to do what comets never do, hold position. As the jets of 3i Atlas locked into a steady rhythm, Earth's upper atmosphere quietly began registering signs that something was responding. It wasn't light, it wasn't particles, it was pressure, invisible but undeniable. On the morning of December 19th, just hours after the object's sunward alignment anomaly was confirmed, the magnetosphere began to tremble, not with impact but with a whisper. A low-frequency oscillation pulsed through the ionosphere, not like the crackling dance of a solar flare but more like a deep sustained hum. One that didn't match any known terrestrial source. NASA's Magnetospheric Multiscale, MMS, satellites, drifting through the tail end of the magnetopause, picked up the signal first. A recurring waveform that rippled not outward but downward, from above, toward the Earth's poles. It didn't arrive with solar wind, it didn't come with charged particles, it didn't follow the rhythm of coronal mass ejections. It arrived in silence. The data was flagged, tagged as anomalous, then rechecked across multiple instruments. The frequency wasn't high, it wasn't sharp or dangerous, but it was consistent, measured, repeating. And it started the very moment the jets of 3i Atlas stabilized and aligned toward the Sun. Now, under normal conditions, a comet's behavior can affect Earth through electromagnetic coupling, especially if the object is discharging massive amounts of ionized material into the solar wind. But this wasn't that. There was no ion tail intersecting the planet's orbit, no burst of charged dust crossing the magnetic field lines. Yet the effect was there, subtle but growing. High-altitude monitoring balloons in the polar regions began recording deviations in Schumann resonance patterns, the natural electromagnetic waves that circle the globe between Earth's surface and the ionosphere. These patterns are typically stable, they resonate like a heartbeat. But on the 19th, that heartbeat skipped, and then it echoed. A second wave began to overlap the first, slightly out of phase, like two signals trying to synchronize. But the new wave didn't come from Earth. It pulsed from above, from a point just beyond the influence of our outermost magnetic boundary, from the direction of 3i Atlas. At first, researchers believed it could be a reflection, perhaps an interference pattern caused by solar wind bouncing off the dense jets of the comet. But the problem was timing. These pulses were arriving faster than any known travel mechanism allowed. They weren't echoes of something that had happened minutes ago. They were near instantaneous, as if the comet, or something near it, was emitting a signal directly, one that Earth's magnetic field could hear, even if our ears could not. Radio telescopes in Chile tried tuning in, listening across a spectrum of frequencies for any burst, chirp, or modulated carrier wave. Nothing. Just the same pressure hum. Low, below the threshold of typical communications, below human hearing, but not below Earth's sensitivity. For hours, our planet reacted, not with weather, not with ground tremors, but with oscillations, acoustic patterns in the sky, frequencies dancing between clouds and ion trails, a planetary ear pressed against space, and the source never moved. 3I Atlas hovered beyond direct contact, yet its presence distorted the very rhythm of our magnetic shield. And then, just after dusk in the southern hemisphere, the humming stopped. No fade-out, no slow decay, just silence. And in that silence a new signal appeared. Not electromagnetic, but optical. A thin thread of auroral activity began spiralling downward from the pole, but unlike any northern light ever seen, it was perfectly symmetrical, circular, like a ring being traced around the planet's crown, and right above it, barely visible to the naked eye, a single pinprick of gold shimmered in near-perfect sync. It was 3I Atlas, now perfectly aligned, now silent, now waiting. As the spiral aurora gently flickered across the polar sky, something shifted within the trajectory of 3I Atlas, so subtly at first that it escaped immediate notice. But by the final pass of the Earth-facing satellites, just as December 19th reached into its last light, the alignment of the object wasn't just sunward anymore, it was locked, perfectly stabilized between two immense gravitational forces. Earth and the Sun, 3I Atlas, had reached what physicists might call a metastable point. Not quite a Lagrange position, and not an accidental drift. This was a deliberate orientation, calculated to hold steady while the object hovered at the edge of Earth's magnetic reach. It no longer fluctuated. The jets that once fired intermittently now moved with mechanical rhythm, pulse, rest, realign. The anti-tail, which had flared green and fractured days earlier, had drawn inward again, and the gold hue along its inner spine had solidified into what appeared, in long exposure imaging, like a segmented spiral. Space telescopes, now fully synchronized across agencies, from the European Southern Observatory to South Korea's KMT net, were all locked on the same coordinates. What they witnessed wasn't just stabilization, it was orchestration. Even as Earth turned and continents passed beneath the comet's gaze, 3I Atlas held its rotational axis parallel to the Earth-Sun plane. Normally a comet this close would be erratic, wobbling under the gravitational tug-of-war. But this object showed none of that instability. It was behaving more like a satellite, more like something that wanted to be still, and that stillness was not without purpose. The particle field surrounding the comet began to thin, not because it was dissipating, but because it was condensing. Instruments that had once registered ionized gas now saw defined packets of mass forming along 3 radial streams. These jets didn't appear random. They emerged from equidistant points around the object's core, each symmetrical, each stabilizing the orientation like gyroscopic arms. And as these arms extended, their tips began to glow faintly. Soft pulses, not in random bursts, but in timed intervals. 4 seconds on, 2 seconds off, 4 on, 2 off, repeated without deviation for the next 32 minutes. Earth's listening post registered the rhythm almost immediately. Deep space radio dishes in California and Canberra reported matching fluctuations in background microwave interference, small amplitude changes but perfectly matched in frequency. These weren't errors, these were emissions, and they were everywhere. Not just directed at Earth, but omnidirectional, like a beacon finally achieving clarity. Not a transmission for us, but a positioning signal, something triangulating, measuring, or waiting. As the hours slipped past and night spread over the Pacific, meteorological satellites noticed something new. Thin bands of polar cloud systems began spiraling in opposite directions. Not violent, not storm-born, just off-pattern, like air masses responding to a change in pressure thousands of kilometers above them. And once again, Earth's atmospheric oscillations began to shift. But this time, the pulses didn't echo. They merged. The magnetosphere, once reverberating under the tension of external influence, now hummed in harmony with the incoming rhythm. Something about the stabilization of 3I Atlas had synchronized with Earth's upper boundaries, not disrupted, not invaded, synchronized. And with that resonance, a final alignment was reached, not just in orbital mechanics, but in the electromagnetic coupling. For the first time since its entry, 3I Atlas was not pushing against the planet's magnetic shell. It was resonating with it, The object had stopped moving in every measurable way. No tumbling, no deviation, no change in signal. It hovered in perfect lock, no longer acting like a comet at all. It had found its position, and for those watching from observatories around the world, there was an eerie consensus. 3i Atlas was no longer arriving, it was already here. By now the object is still holding its sunward-facing alignment, and that alone should concern every observatory still watching, because natural objects don't lock into position like this, especially not under the stress of solar radiation, gravitational turbulence, and interplanetary motion. Yet 3i Atlas did. It aligned. And more importantly, it held. Not with erratic tumbling, not with chaotic drift, but with the kind of smooth correction you'd expect from a probe or satellite receiving guidance. No one is claiming certainty. The official data packets from NASA, ESA, and private observatories remain filled with careful language. Words like anomalous, unexplained, inconsistent with prior behaviour. But the silence speaks louder than the words. Because in the hours since this alignment occurred, there's been no attempt to redirect the narrative. No suggestion that this was noise, no claim that it's routine. What we've witnessed today is a kind of cosmic pivot. The object that entered our system as an apparent comet is no longer behaving like one. Its trajectory is still inbound, its emissions are still increasing, and its behaviour has crossed the threshold of explainability. It's acting like it knows something. And now all eyes turn to the next 24 hours. Will the alignment break? Will it shift again? Or is this the final configuration before something even more significant takes place? If you've been following this story, now is the time to stay locked in. Because this isn't a drift, it isn't a flare, it's an alignment, and alignments usually mean intent. We'll be watching, we'll be listening, and when the next shift occurs, we'll be ready to tell you what it means. Make sure you're subscribed, because this is just the beginning.